that's me. I'm Godfrey. Nice to meet you all and people watching from the internet. Um, you can find me on the internet as Chenkin Code. Um, I just want to give you a warning that we have a lot of talks today, and this is probably going to be the most boring talk. So if you're watching on the internet, feel free to tune out for an hour and come back for the other talks. And in particular, I just noticed that earlier before the start of the meetup, there's going to be a talk about networking later today, and that's a topic that I'm really interested in. So yeah, I'm really looking forward to that. Anyway, I have been here before once for the Seattle meetup, and so it's great to be back. I really like coming back to Seattle because the people here are really nice. This morning, I was meeting up with Chris, and then he was like, you're in Seattle. I need to show you around, and let's go get coffee. And he keeps telling me on our way there how this is like Seattle's best coffee. And then I was really excited. So we got there, and we ordered our coffee, and it was amazing. Looks like that. I think it's called what was it? The Cafe Nico? Something like that, and it's basically an espresso with half and half and some orange zest, something like that. It's great. You should try it. But that's amazing. But then I was really disappointed in the end because it's not Seattle's best coffee. I thought that's where we're going, and we end up getting the other thing, which is nice, but it's not that. Anyway, I should tell you a little bit about myself before we start. Probably not a lot of people know this, but I'm actually a professional Go player. I'm an internationally recognized professional level 7 Go player, and I just started this week, basically, and I think I'm pretty impressed by my progress so far. So that's my full-time job, and I'm really excited about this career change. Part of it is I get to do what I love to do for my day job, but the other part is I finally have a reason to go to the gym every day. This is me going to the gym yesterday. And so even though it's great to be a professional Go player, it could be pretty frustrating at times. And if you have tried it, you probably know a lot of times you see this screen, which is basically the server not working, and it could be very frustrating because, like, guys, I need to work, and this is not working. It's like when your VPN is down, right? And every time it's this, I'm like, this is 2016. How hard is this? I thought we figured this out. Like, you gotta catch them all. Anyway, so that's my work, and my hobby is an engineer at a company called Tilder in Portland, Oregon. We have a product called SKYLIGHT, and it's basically a performance monitoring solution for a Rails app, and it gives you advices on how to improve it. You can sign up at skylight.io. Like I mentioned, it's only my hobby, so the only way I get something out of this is from the referral credits. So if you could sign up with this link, I would really appreciate it. Yes, take out your pen and paper, write that down. I'm serious. All right, unless you're from the United States Citizenship and Immigration Service, in which case that was a joke. I do work at Tilder as a full-time employee, and they do pay me in real money, so please do not pay my visa away. Also, if you are from the IRS or the CRA, please note that SKYLIGHT credits have no cash value and should not be considered a form of income. Anyway, you should sign up. Even if you're not using Rails, we have, for our customers, we have a newsletter. Once you have signed up, you can go to your preference and you can select your email preference. There's a thing called the Insider channel where we basically write about random stuff every day. That was me writing one of the issues, and a lot of times I end up writing about Ember and stuff. So if you're curious about what we do, like on a day-to-day basis, you should sign up with that referral link, and choose the daily, the insider email option. So with that out of the way, actually, before we talk about Glimmer 2, I would like to mention that LinkedIn and Tilder has been pretty generous in sponsoring my time and Yehuda's time to work on the Glimmer 2 project, and this is probably not going to be possible without their help. And you probably recently heard that Microsoft bought LinkedIn for 26 billion, and a lot of people are very confused, like, that sounds like a lot of money. Where's that valuation coming from? Well, I think people, like the analyst is just not very careful with the due diligence, because if you look at their assets, one of the things that's ranked highest on the list is basically they trademarked the most punnable two-letter word in the English language. If you walk around the office, you will see this everywhere. They basically have in puns and in other places. But I thought, well, maybe like more people will need to know about this, but at the same time, I think even LinkedIn internally, no pun intended, didn't quite realize the full potential of their assets. So I decided to give them a little bit, some suggestions. For example, I think they should probably paint that at the parking lot, and I think their design team should probably be renamed, and the website could use some work. And if you have been watching TV, they have an ad campaign on YouTube and stuff, but I think that could probably be better. Finally, with the Microsoft acquisition, I think there's probably some opportunity there. So there you go. So with that out of the way, I hope to mainly thank you, LinkedIn, for their contribution. And I heard they are hiring for the apps team, so if you would like to work for them, maybe you should talk to Chris. One of the coolest thing about working for a company like LinkedIn is you're literally building a professional network. So if you would like to connect to my professional network, you can email me at that LinkedIn email address. The last time they sent something there was they needed me to run some security update on my LinkedIn laptop, which I didn't actually use, and then that go on unnoticed for a few months until they emailed my manager. So if you would like to get in touch with me, that's probably the best way. Anyway, so with all that out of the way, we can talk about Glimmer 2, and that's basically the fun part of the talk, and the rest is very boring and very technical. I decided, instead of talking about Glimmer 2, I decided I would actually tell you a little bit about programming language implementation. The reason is not to help you become a VM hacker in this 45-minute slot, but I hope what you would get out from this talk is to have a rough mental model around some of the tools that you're using every day at work. And hopefully I can convince you that these kind of things are less scary than you think, and learning about these obscure or niche topics could actually surprisingly sometimes help you solve unrelated problems in ways that you don't expect. Before we can talk about that, we need to get some definitions out of the way. So the first thing is a compiler. So that's a pretty scary sounding word, but a compiler is basically, at a very abstract, high-level sense, is basically just a program that takes some input and produces some output. Now, of course, that in practice basically describes all programs ever, so you need to get a little bit more precise than that. So a more precise definition for compilers is basically a program that takes other programs as input. So it takes, so it is indeed a program that takes some input and produce some output, but the input is very special. The input is a program. And the output is also a different program. So basically it's a thing that takes a program as an input, do some transformation on it, and output a different program. Now, I was pretty careful with my words there. I said like a takes a program as input. I didn't say it takes source code as input because while that is often true, it's not necessarily strictly necessary that you take the source code string as an input to a compiler. You might think, oh, a compiler is basically the thing that turns my C code into an binary executable. But that's a very narrow definition of the word compiler. But the word compiler is actually an umbrella term that basically covers a lot of things, like even you might not know this, but you probably used a thing called Babel, which is the program that lets you write ES6 syntax in your Ember JS code, like you can write classes or arrow functions. And Babel is the thing that turns it into ES5 code, which is what your browser could natively understand. You probably have been calling Babel a transpiler, and you might be thinking that, oh, a transpiler is different than a compiler. But actually, they're the same thing. A different name, an alternative name for a transpiler is a source-to-source compiler. Basically, you take some source code, and then you compile the source code and spit out some other source code. Okay. And there are other kind of programs that you probably use, but not necessarily think of them as compilers. For example, you probably use a minifier or concatenator to build your apps. And there are other more obscure things like if you use Go or Rust or some other languages like that have tools that format your source code according to, like in Go, that's GoFMT, and Rust, there's a similar thing. But it basically takes your source code and resave it with the community convention and standard. Right? So that's also technically a compiler, and there are other things like compiler or decompiler, which fall under the rough umbrella of taking programs and turning them into different programs. But it's not necessarily the GCC or the concrete understanding of compiler you're used to. So now that we roughly understand what compilers do, the natural question is, why do we need them? Why do we need to compile stuff? Right? The naive answer is, oh, you need to compile your program in order to run it. But that's not strictly true. That's not actually true. But to understand why that's not actually true, we need to break this down a little bit to understand how compilers actually work. So if you break it down, a lot of people will give you this kind of diagram. So basically, a compiler can be split into two halves. There's a front end and there's a back end. What the front end does is, the front end is also called a parser, and the back end is usually called a codegen. So the parser basically reads the input program and turn it and massage it into data structure that is easier to work with. So a lot of times your compiler might be taking source code as like strings as input, and that's not very easy for a computer to work with. Right? It's just a big blob of text in a file. So the front end, the parser, basically reads that source code or whatever input format it came from, and it turns into a more convenient data structure, maybe a abstract syntax tree, or in the more generic sense, it's called intermediate representation. That is a fancy word that doesn't really mean much. It's just some data structure that you prefer to work with over the source, the original input. So it could be, like I said, it could be a tree, it could be an array, it could be many combination of things. But this particular word, the IR, internal representation, is going to come back a few times today, and it's like good to remember that, oh, it's not something scary. It's just a data structure that is easy to work with. So the second part, the backend or the codegen, basically iterates through the data structure and emit the output program that you want. So in the case of compiling your C code to binary, it will basically loop through that IRL and then generate machine code. In the case of Babel, you basically walk the AST and then you emit the corresponding ES5 code. Right? So that is probably the more interesting part of the compiler compared to the parser. So now that we understand what the compiler is doing, there's actually an alternative to that. So instead of taking the IR and turn it into the output program, now that you have understood what the program is talking about, you can actually just write a thing that does exactly what the program tells you to do, because now you can understand what the AST nodes are talking about, or what the IR is actually describing. So that's called an interpreter. In the high level, basically, you take the input program, and instead of emitting a different program, you basically just run it. So you are, you're probably familiar with this in terms of scripting languages like in Python or in Ruby. You usually have an interpreter or an interactive interpreter that you can play with. But you can actually write an interpreter for low-level languages like C as well. Basically anything you can compile, instead of compiling that to disk, you can of course just write that into memory and tell the computer to please run the code I have in memory. So that would be a very naive way to implement an interpreter, but you can intuit based on that, oh, actually, I don't have to compile, I can always interpret. So that's all we're going to talk about for interpreter, but the question is, if it's always possible to interpret, then why compile? Like, why is it needed? So there are a lot of reasons to do that, but I think a high-level framework for thinking about that is having a compiler allow you to front-load some repeated work and do it once, pay the cost once at compile time, to reduce the cost you have to pay at runtime. So it could just be rearranging things into a more efficient format for runtime, but very often it could also be an explicit optimization pass. Basically, once you parse the source into a convenient data structure, the IRL, you can run it through an optimizer. For example, you can see that this function is never used anywhere, so let me delete it from the IRL. Or you can see that this function is called a log, but it's very short, so maybe you can just inline this function into all of the call sites, so you don't pay the cost. You don't pay the cost of a function call at runtime. So that's roughly what a compiler is good at doing. Basically, there's some kind of work that you do repeatedly at runtime when you run the program. But if you have a compile phase, you can try to do some of the work upfront, so you don't keep paying that cost over and over again when you run the program. You can intuit this in terms of, for example, in your build process in your Ember app, so you're basically minifying your stuff, right? So that is not doing something very interesting, but you are basically realizing, you actually don't need the full, to the computer, like whether you name the variable 18-character name or a single letter doesn't make a difference. So you can just do the shorter thing and you have a more efficient thing to send down the wire. That's not exactly optimization per se, but it's giving you an intuition of the kind of stuff you can do ahead of time so that at runtime you don't pay the cost. So, so that's all we're going to talk about for compilers. So now let's get back to templates. So what does all of that have to do with rendering templates, which is what Glimmer is supposed to do for us? To talk about that, in case some of you are not very familiar with Ember or not, so I guess I should quickly walk through some of the features you have in the templating layer in Ember. So Ember uses handlebars for templating, and this is what a handlebars template looks like. It might look pretty familiar to you, it might look like HTML because it actually is HTML. But of course, if it's just strictly HTML, then it's not very interesting. You just use HTML. So on top of that, it also has other more interesting features, like you can have a variable, right? So instead of hard coding hello something, you can just look that up dynamically. And render a personalized message here. There's also helpers, which is basically functions that take some input to format things on the screen. And finally, there are also components. So for example, you might be using Font Awesome for your icons, but then the I tag is very annoying to type, so you can abstract that into a component that is easier to invoke. Of course, you can do fancy things like having behavior around them and yielding content and stuff, but that's the basic idea of components. And actually, finally, there are also some control flow you can do in your templates. So there's the if helper, which basically do what you would expect. It toggles based on a condition that you pass in. And there's also things like loops, which is the each syntax you see at the bottom. So that basically takes a long list of users and repeatedly render a list item for each user. So based on this, you can probably realize that templates are actually just programs. They are a specific, very specific kind of program, but especially given this, you can see that it's not that different from the regular kind of programming language you're dealing with. It's things like control flow. The difference is basically it's a program that describes how you would like to render stuff into the DOM. So since templates or handlebars templates are just programs, it would make sense that we basically go look at how people have been, basically look at the work of people who spend their entire life implementing programming language and see what kind of ideas we can take from there to help us solve the templating problem. So, for instance, handlebars always had the concept of a compiler, and since the very beginning of the project. And in fact, that is the main reason for handlebars to exist. So there used to be a thing called Mustache, which has a similar syntax, but it doesn't have a compiler. So what you would do is you would, at runtime, every time your user visits your page in the browser, it would, and you would like to render a Mustache template. What you would do is basically you run that against some regular expressions and you substitute stuff in there dynamically. So that's not very efficient. And remember, compiler, so the problem is while the handlebars template or Mustache templates are very, very readable, very human readable, it takes a non-trivial amount of work to parse the templates for the computer to do useful stuff with it. You can use regular expressions, but that is also not free and pretty slow in practice if you have a lot of large templates that you want to render. And remember, while compiler is a very scary word, it's basically just a program that takes some program as input and transform it into a different format. And the point of doing that is to remove some repeated work at runtime and move it, like pay the cost once at compile time. And that's exactly the kind of stuff that we're looking for here. The handlebars compiler basically allow you to take a template string and run it through a parser and generate a JavaScript, basically compile the template into a JavaScript function. So you do handlebars.compile and you give it the string, then it basically do the back-end, front-end thing. It parses the handlebars template into an AST, and then from that AST it generates a JavaScript function. So what you get is you basically get a function that you can call with the context object, and it will automatically return a string for you with all the curlies filled in. So even better than, so that has the obvious benefit of if you are about to render the template many times, perhaps your template is an item, like a row in a very long list, right? And you're gonna invoke that template many, many times. So by pre-compiling it, you basically pay the parsing cost once, And then once you have done that, then you can just keep calling the function, and it will be relatively fast, or at least you don't have to, like you're just paying the rendering cost and not the parsing cost per row. But even better than that, the handlebars compiler actually runs on the server. So what's actually happening is before you publish your app, you run it through the build step, and basically on your computer or on your build server, you run all your templates through the handlebars compiler, and what you get back is a bunch of JavaScript files, right? So as far as your users is concerned, when they go to your website, all they're doing is they see a script tag, like maybe templates.js, right? You would go to the server, get that JavaScript file, and download it. To the user or to the browser, that is not any different from any JavaScript files that you have. Right? You just happen to have like maybe 10 or 20 functions in there that you can call that happen to do what the template is supposed to do. But that's great because no users actually ever have to pay the parsing cost in their browser. Right? That cost is already paid upfront by your build machine or by your own machine or by your server. So it actually is, not only does it save the repeated invocation costs, it also saves the parsing cost for every single one of your users, and that adds up very quickly, and it's a big win. So that's handlebars. Modern Ember actually does more than just using the handlebars compiler. We basically have a spec-compliant HTML parser, and that's called the HTML bars project, and you are around for long enough to remember that. But what that does is basically parses your, it not only parses the curlies, like the handlebar syntax in your templates, it also parses your HTML code in your template. So basically what it does is on the server side, or on when you build your templates or when you build your Ember app, it basically converts all of those HTML stuff, the HTML strings, into DOM code and emit a JavaScript function, more or less. Right? So instead of shipping a string with angle bracket A something something, it would just have a function that has document.create element A and then like A.set attribute something something. So it does the parsing work upfront and ship a compiled thing to the client. So that's Ember today, or that's Ember and HTML bars today. So that all sounds great, but there's one problem. The problem is the handlebars language is very simple. There is basically only curlies, curlies, and curlies. Concretely, what I mean is that here, in this template, this is the handlebars template. If you look at this and you see that there's curly, curly name, curly, curly in there. So what does that mean? Well, unfortunately, without knowing much about the environment, you cannot actually tell ahead of time whether this is talking about a local variable lookup, or if it's a helper that happens to not take any arguments, or if it's a component that happens to not take any arguments. So unfortunately, all of those information are only available at runtime. Basically, it needs to do your app to run all those registrations to know that. And the server or your Ember CLI, the build step, doesn't really have those information. So therefore, in practice, even though we do a lot of work to pre-parse the syntax and the HTML at build step, and we compile that into a JavaScript function, which sounds very fast. Unfortunately, because there's not much we can do about these at compile time, what ended up happening is a lot of things, most of the interesting things actually happen in the curlies, right? That's why we're writing handlebars, not HTML. And because all of those things, like we can't do much about them on the server side, they all end up going through some very generic JavaScript hooks at runtime. So even though you do indeed produce a function for your template, what ends up happening in that function is you call a lot of other functions that are very generic and very dynamic, and you have to do all the resolution at runtime. which defeats the purpose of doing stuff upfront. Rather, it's not doing a lot of stuff for you upfront because all the interesting work still happens there at every time you invoke this template. So usually that is not a very big problem, but when you have things like loops with a lot of items, it starts to add up, right? Like every time you execute this line, or in the case of a loop, every time you execute one iteration of the loop, you have to ask the question, is name a component? Is that a helper? Or is that a local variable? Is that something else? So this is not the only problem, and this is probably by far not necessarily the most expensive part of the system, but this gives you a good intuition of the kind of problems we have today. Right? Basically, we don't have a step that lets us front load the work, so we end up doing that every single time we invoke something. And in this case, every single time we invoke a block inside the loop. And the fallout of a lot of these problems is that rendering components is quite slow in Ember. Now, again, I'm not saying literally looking up the thing is what makes rendering components slow, although it does contribute to that somewhat. But the kind of problems we have are pretty similar in nature to this particular example. So again, this is not enough to be a problem for a lot of apps, but unfortunately, Ember is positioned for building ambitious apps, and a lot of big teams like LinkedIn and Twitch are building very big apps with Ember. And on big apps, this really started to add up. And this is quite unfortunate because everyone loves component. That's one of the main reasons people love Ember. If you're not familiar with the idea of components, you can think of them as a refactoring tool. When you're writing JavaScript, if you have a very long function, you probably want to break it down into smaller functions, right? Or if you notice that you have repeated the same few lines of code in a lot of places, you probably want to extract that into a helper function that you call in all those places. So a component is pretty similar to that, right? So if you have a very big template, you probably want to split that up into pieces. Or if you have a widget that you use in a lot of places, you probably want to turn it into a component. And because given that very important role, you can imagine why it would be bad for components invocation to be slow. It's like if you're programming a language where function call is expensive, then every time you want to, like every time you write some code, you have to decide between whether I want to write nice, readable, maintainable code, or whether I want it to be fast and just manually inline all the things with your big function. Right? So when component is low, it's kind of like that. You end up in a situation where this would be really nice if I can abstract this into a component, but unfortunately this is too slow, so I cannot do it. And that would be quite unfortunate. So that is, among the things, fixing component is one of the main goals for the Glimmer 2 project. And we did a few things in many fronts to address that problem. And today I'm going to focus on one particular line of work. And so the solution is, since we agreed that templates are programs, we should just look at what programming language implementers do to make things fast for the programs. So one line of idea is called adaptive optimizations or runtime optimization. The idea is that in general, there is a lot more information available to you at runtime that you can use to optimize your program versus compile time. So therefore, instead of betting too hard on doing the right thing at compile time, you can just collect up those information at runtime and optimize your program accordingly, using those information as feedback for your optimization process. So in our example here, we actually know that once we have figured out whether name is a local variable lookup or whether it's a helper or a component, we still have to ask that question, right? But once we have asked that question at any time after you booted your app, that answer is not going to change, because basically we consider the registry frozen, right? So you cannot add more stuff to it. So once we determine the type of this curlies, we don't have to keep asking the same question over and over again. So, so concretely, once we know that, for example, name is actually a local variable, it's not suddenly going to turn from a local variable into a helper like during the middle of the loop, or when you transition away from this route and you come back to this particular template, the answer is not going to change. Therefore, it seems pretty silly to ask that question over and over again, whether it's inside the loop or whether you navigated away from this page and came back. So the solution is, if you remember, compilers are basically for taking out the repeated runtime costs and moving it up front and paying the cost only once. So our solution is basically we added a compilation phase, a runtime compilation phase to solve these kind of problems. So again, this particular thing is not the most expensive thing ever, but it's a pretty good example for understanding the kind of trade-offs that you can make. So instead of, like, if you remember, today we basically look at your templates, parse it on a build time, and we basically generate a JavaScript function and send it down the wire. So instead of sending down an opaque JavaScript function, what we did more or less is we just took the IRL that we have at the build time. So the server IRL is actually the build time IRL. So if you remember, the compiler has a front end and a back end, and the thing in the middle is the IRL, the intermediate representation. So instead of taking that intermediate representation and turning that into a JavaScript function, what we did is basically we just serialized that into JSON, more or less, and we send that to your Ember app at runtime. So instead of getting a bunch of JavaScript functions from your server, you're now getting a bunch of JSON strings. So what we do with that is, before you invoke a particular template, which is now represented in JSON, for the first time, before it's used, the template is used for the first time, we will compile that at runtime. The advantage of that is, at runtime, we have a lot more information to work with. Among other things, we know exactly what each name referred to, whether it's a component, a helper, and other stuff. So this kind of compiler is often called a just-in-time compiler or JIT compiler. It's, once again, a very fancy word, but basically means you compile it just before you use it. So in this case, we compile the template just before we are about to render it on the screen. So, like I said, this compiler allows us to use the runtime information we have to do the triage work, triaging the curlies among things, and it also allows us to produce specialized and more optimized code based on what we know at runtime. So now that's the left side of the equation, right? The other side of the equation is, okay, a compiler is a thing that takes something as input and outputs something else. So what is that output? What do we compile the templates into? Now, we could just compile that into JavaScript like we did before, but it actually gets pretty complicated and pretty expensive to do on the client side, and you don't actually get that much gain from it. And actually, it might very well backfire due to other reasons that I don't have time to talk about. We can talk more in person after. So instead, there is a more direct way to do it. If you remember, in the beginning, we have a compiler, which is the thing that turns into some program. But then there's a more direct way to do it. Once you have parsed something, right, like once you have an intermediate representation, you can just execute that with an interpreter. So you don't actually you don't always need to compile it into JavaScript. You can just write an interpreter in JavaScript and just interpret the IRL. And so that sounds very, so basically what we did is at runtime, we compiled that into stuff we call opcode, and we feed that into the runtime VM that we run in JavaScript. So that sounds very fancy, but a VM is basically just a rebranded version of an interpreter. A VM is an alternative name for a VM or a virtual machine is a bytecode interpreter. And it has a word interpreter in there, so you know VM is just an interpreter. It's interpreting a very specific kind of thing called bytecode, but that itself is also a fairly meaningless term. And actually, a lot of time you will see that bytecode is basically just a synonym for IRL. And once again, IRL, intermediate representation, is just a very loose term to talk about some data structure. So what we're really talking about here is our runtime compiler turns our templates into an array of instructions, more or less. And we will look at that example, but the takeaway here is, oh, like Glimmer has a VM, what does it mean? Well, actually, it just means it loops through a bunch of instructions at one time. And so here is a more concrete example. So let's say you're invoking a component called hello-world. So that the top is where you call this component. This is how you invoke it. And the middle is the layout of the component. So this would be, in Ember, this would be app/templates/components/hello world.hps. Right? So this is what you put inside the handlebars file for the layout. And then at the bottom, that's the output. If you look at your Chrome inspector, that's probably pretty familiar. Basically, even though you don't have anything in the layout, automatically Ember gives you a wrapper around your component if you didn't specify it as a div, right? And also automatically give it an ID, and also it automatically give it a class name called Ember view. So even though your layout is pretty simple, this is the output you get. So if you look at so like I mentioned, this is the middle thing is what we're focusing on right now. So the middle layout or the template for this, the layout is the template for the component, right? So like I mentioned, the template needs to be compiled before we can render it, and we compile into the Glimmer opcodes. So what does that look like? So this is stuff I copied from Ember Canary today. I actually tried running code in Canary and then I took this out. So this is the list of opcodes that the component layout compiles into. And if you remember, it's basically just the word hello that compiles into this. Now, it doesn't literally compile into this thing. It's not like it doesn't compile into these strings, right? This is just a visualization of what the objects are like. But basically compiled the template into an array with 17 instructions in there, and each instruction is talking about a pretty focused task. We don't need to walk through all of them, but roughly, first, it basically look up the tag name from the component instance. Right? Tag name is a property on all components, and if you didn't specify, we'll use a div. Otherwise, it will use whatever tag name you have on the component. And then also Ember has a feature where if you do tag name equals empty string, it actually render what we call tagless component. So it doesn't give you the wrapper around your component. And then we basically render the div on the screen, and we call it the create element host, and then we install the Ember ID and the Ember view class on the div. And then there's something to do with aria role. And finally, on line 12, we finally put the string hello on the screen, right? So that's line 12 is appending a text node with the string hello in it, which is what you actually have in your template. That's the only thing you have in your template. And then finally, it does more stuff with the tag name. That is to handle tagless components, basically. And finally, it closes the div on line 16. So this actually is, this looks pretty complicated, but if you understand the concept, it's basically turning your templates into some very atomic instructions. Atomic is not a very precise word, but it's basically turning your template into an array of very specific instructions, each focusing on doing a very specific task. And the nice thing about this is it's very easy to visualize what kind of work is involved in rendering a component on the screen. Right? So you might look at this and it's like, it's just hello, but actually this is all the work that needs to happen to render the hello component on the screen. Another advantage of this is makes it very easy to debug. So in the current implementation, it's basically just some ad hoc functions calling other functions, and it's very hard to trace down where things are happening. Whereas with this, the VM is basically just an interpreter loop that loops through each of these instructions and call. Like you can imagine, these are basically 17 functions in an array, and the VM job is basically just take one element from the array, call the function, and then take the next element and call the next function. So to debug this, you basically just need to set a breakpoint in the interpreter loop, and you can see exactly what instructions it is running and where things went wrong. It also makes it very easy to measure the cost because you basically just do a profile, or you can wrap each of these things with a time function. You basically just do a profile and then see what kind of outputs jumps up in the profile. This is, then that would be an area that perhaps needs some work. And finally, it makes it easy to think about how to optimize things. Specifically, what I mean is that if you look at these 17 opcodes, you realize over half of them are related to features not used in this template. So the reason we need to have an open dynamic primitive element there is because you have, in Ember, components can have a tag name property. That is usually something that's on the class, right? So you do component.extend, and then you put tag name in there. So if that's the only thing we need to support, we can actually just look at the class at compile time, and we can just compile the tag name into the instructions. But the problem is, historically, because we are not doing that kind of work, so whether it's intentionally supported or not, you can actually, when you create a component, you can actually pass tag name dynamically, either in the template syntax, or you can, in the constructor, or in the init function, you can actually set this.tagName equals something dynamic. That is, like, you can basically do this.tagName equals math.random, right? And that's something. So unfortunately, there are a lot of things like that that's very dynamic, and you cannot tell statically by looking at the component class. ARIA row is another example. So there's an automatic binding from row to ARIA row with attribute, and because you can set all these attributes when you instantiate the component, we actually don't know whether we need them until we actually have the component instance. So this gets you thinking, oh, it kind of sucks that, so by the way, I'm not implying these are actually expensive or the most expensive thing about component creation, although it is somewhat expensive. But it gives you, like, it basically gives you a mental model of, oh, like it is doing some unnecessary things, right? Like it kind of sucks that even though a lot of your components might not be using these very dynamic features, but you're paying the cost for them all the time. So the way to think about optimization is basically, oh, is there anything we can do to remove these opcodes from most components, right? So if you don't have these opcodes, then you're definitely not paying the cost, right? Like, because the VM is basically just looping through whatever is in the array and execute those stuff. And if you have less stuff in the array, that's less work. So Glimmer makes it possible to start doing those kind of optimizations. So for example, one of the things that I was talking with Chris today is perhaps we can just optimistically assume your component is not using these features. So we can always compile a version without all these things, but right before we render the template, we can have an assertion that checks whether the template we compiled is still valid for this particular instance, right? So, for example, the first time we render a component, we have the instance, so we can see, this component instance has the tag name diff in there. So we're just going to assume all instances of this component would have a diff. But then, as soon as you see a different instance later have a dynamic tag name, for some reason, you can just fall back to the, like you can just recompile the thing into the more generic version. So for most of your components, if you're not using these features, you get the fast, small set of instructions. But if you're using those dynamic instructions, then you basically pay the cost of those features as you use them. So you basically opt into using the more expensive features instead of making everyone pay for them, regardless of whether you're using them. And that's great because it ties into the bigger picture. So that's a very specific example. And once again, I'm not making any claims that this particular thing is a high priority thing to optimize, but it does give you a good understanding of the kind of optimization you can do with this kind of setup. So it's great that Glimmer makes it possible for us to support some of these legacy functionalities in a more pay-as-you-go manner, because it ties into bigger ideas. Like in Ember, we take backwards compatibility very seriously. So it's not like we don't like that dynamic tag name feature, so we can just drop it in Glimmer too, right? Like it or not, some people use it today, and we have to keep supporting them. But with a foundation that allows us to make things more granular, makes things more opt-in, we can more easily support our legacy baggage without having to make everyone, the entire community, pay for that cost. And this is basically stealing ideas from the web platform, right? So in JavaScript, there are a lot of slow features that are extremely slow, but most people don't use them. So JavaScript engines figure out ways to basically pretend those features doesn't exist until you actually use them. So compile your JavaScript assuming that you don't use those expensive things, and if you actually use it, it basically de-ops your function and compile into the slow thing. And that basically makes it cheaper for most people, and if you do need it, it makes the cost a little bit more opt-in. So that's it for the technical part. That's the Glimmer part. Actually, that thing I showed you here today is not the cool part. So far we have only been talking about how to render a template on the screen. Unfortunately, that is not actually very interesting because everyone knows how to do that since even the handlebars are backbone days. What everyone has been trying to do efficiently in the last few years is basically keeping the templates up to date. Right? The key here is when you use handlebars, when you use Ember, when you change some data, you expect the template to update along with that. So that's actually where we have the most breakthrough with the Glimmer system. I don't have too much time to go into that, unfortunately, but the idea is basically as we do the initial render, the append VM is actually also a compiler that is compiling a specific update program for a template. So basically, when we render stuff, we see what actually needs to be checked and updated at update pass, and we compile a special program that is much smaller than the append program just to do those checks. If you want to learn more, we can chat after. And also, actually, Yehuda and I did a talk at EmberConf about some of these things, and I believe Yehuda this week just reported a deep dive on the Glimmer 2 internal, so maybe you can look at that as well. So finally, I think I'm super out of time, so I'll just go through this very quickly. What does this mean for you? I think in the short term, you can expect some performance gains when Glimmer 2 is initially available. I think you can expect some performance gain for your app with much more to come in the future. So since EmberConf, our focus so far has been compatibility and integration, right? So optimization is not necessarily the highest focus, but I hope I have convinced you that we have some pretty cool infrastructure for doing more of that in the future. And in addition to that, it has a much better foundation for future performance and future work, and it unlocks some long-awaited features like Glimmer components, also known as angle bracket components. So next question is, when is this happening? The official answer is soon, because this is recorded and broadcasted to who knows how many people. I don't want to commit the entire core team to a specific timeline, but soon we will have an alpha build for Ember plus Glimmer. So the intent is that if you, so first of all, you can start playing with that in your app, and if you see anything broken, you can report it. But more importantly, if you are a maintainer of some ecosystem pieces like add-ons or things like Ember Twiddle or the Ember Inspector, you can start working with these alpha builds to check that your piece of the ecosystem is working and report any incompatibilities. And we expect that basically to work alongside the usual beta cycle, so maybe we'll do one release per week or something like that, so we keep slurping in the bug fixes, and so you can keep retesting your stuff to make sure they're still working. And finally, how do you prepare your app for it? The answer is roughly nothing. Like I mentioned, we did one of these transitions before when we switched everyone from handlebars to HTML bars. So now that you probably understand the change better, we changed from a totally string-based templating engine to a DOM-aware engine. And that was a pretty big change under the hood, but for the most part, things worked for most apps. So we're definitely aiming for that kind of transition, so we take backwards compatibility very seriously this time, and we hope that you will be able to just literally drop it in, turn it on, and start getting the benefits from this. And so how do we get there? How do we make sure it works for most people? The answer is tests. We have a lot of tests, and we have written a lot more tests since we started integrating. I think a lot of people here, Dave, for example, have seen a few months ago around EmberConf time, we have a request issue that invited our community to help us port the existing test to a new testing infrastructure. What that did is it allowed us to run the existing test suite, and also at the same time we beef up the existing test suite by a lot. But what that did is it allowed us to run all the entire rendering suite in Ember against both the current engine and the new engine simultaneously. So we actually have been doing that on CI for a few months now. So what that does is basically, if the test pass, and the test, basically it tells you something when the test fail in either of the engine, right? Like if it fail on Glimmer but passes on HTML bars, that probably means there are some incompatibilities in Glimmer that we need to fix. On the other hand, if it only passes in Glimmer and fail on HTML bars, that probably means we wrote the test wrong and we're not covering the current semantics very carefully. So by having our test suite runnable on both systems, I think gave us a pretty good measurement of how we're doing in terms of compatibilities. And finally, I will also like to mention quickly that the Glimmer 2 project is done in TypeScript, which is quite handy for these kind of big projects. And I would like to talk more about that, but I'm out of time, so maybe we can chat about TypeScript later. One last thing, I don't know if you noticed, but I have this really cool t-shirt here, and I would like to collect more selfies with people I meet, so if you don't mind, you should come talk to me and we can pick some hashtag solo selfies. So that is it for my talk. Once again, I'm Godfrey. You can find me on the internet as Code, and thank you for your time.